Hello, it's me, Maria Sandoval, and today I will be talking to you about thermochemistry and a few of the laws of thermodynamics. So, we're starting with the sign conventions for Q, W, and DE. And Q plus W equals DE. So that's what we're going to be going over in our graph today. So if you have a positive Q plus a positive W, you get a positive DE. If you have a positive Q plus a negative W, your DE depends on the sizes of Q and W. And if you have a negative Q and a positive W, it also depends on the sizes of Q and W, and if you have a negative plus a negative, it gives you a negative DE. For Q, the plus means that the system is gaining heat, and the minus means that it is releasing heat. And for W, the plus means that there is work being done on the system, and the minus means that work is being done by the system. So, the law of energy conservation. The first law of thermodynamics states that the total energy of the universe is constant. Number 1. Energy of the universe is conserved and neither created nor destroyed. So you can't get rid of energy, it only gets moved around. Energy of the universe is transferred in the form of heat and or work. So DE universe equals your DE system plus DE surroundings, which equals 0. Moving on to the units of energy, this is the formula I was just talking about. The SI unit of energy is the joule, J. So 1 joule equals 1 kilogram times meter squared times S squared. The calorie was once defined as the quantity of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. But now, which means that 1 calorie equals 4.184 joules. The British thermal unit, BTU, is often used to rate appliances. 1 BTU is equivalent to 1055 joules. When gasoline burns in a car engine, before I start, let me explain that we're going on to a sample problem that's going to help us determine the change in internal energy of a system. So when gasoline burns in a car engine, the heat released causes the products CO2 and H2O to expand, which pushes the pistons outward. Excess heat is removed by the car's radiator. If the expanding gases do 451 joules of work on the pistons, and the systems release 325 joules to the surroundings as heat. Calculate the change in energy, which is our DE, which was what we were talking about earlier. And we're calculating it in joules, kJ, and kcal. So our plan is to define the system and surroundings and assign signs to Q and W correctly. Then D and E equals Q plus W. The answer can then be converted from J to kJ and to kcal. Heat is given out by so for our solution, we're looking at it, and heat is given out by a chemical reaction, so it makes sense to define the system as reactants and products involved. The pistons, the radiator, and the rest of the car then comprise the surroundings. Heat is given out by our system, so Q equals negative 325 joules. The gases expand to push the pistons, so the system does work on the surroundings, which W equals negative 445 joules. So here we have our joules, which we just got, is negative 76 joules, and we're going to times that by 1 kJ over 10 to the third joules so that we can convert it to our kJs, which gives us the negative 0.776 kilojoules. And DE equals Q plus W. So what we're doing for that is the negative 325 joules plus negative 451 joules, which gives us our negative 776 joules. We're putting that here and we're multiplying by 1 kcal, and we're dividing that by 4.184. kilojoules, which equals our negative 0.15 kcal, because we're converting to kcal. I'm sorry that I jumped ahead to this, but you're going to need to get this done before you move on to this so that you can have these numbers for these equations. So moving on, enthalpy is a chemical change at constant pressure. So dE equals Q plus W. To determine the dE, both heat and work must be measured. The most common chemical work is PV work. This is work done when the volume of a system changes in the presence of an external pressure. Enthalpy, H, is defined as E plus PV. So dH equals dE plus dPV. So if a system remains at constant pressure and its volume does not change much, then dH is just about or around equal to dE. Moving on, this is going to be our last slide. Two different paths for the energy change of a system. So here we're looking at pressure, volume at work. So even though Q and W for both two paths are different, the total dE is the same for the both. You see here, E is released as work and heat, and E is released as heat here. Here you have a trash can burning off some things. Here you have a car leaving its exhaust out. In this, you have your reactants as CHH18, which is octane. And then your product is 8CO2 plus 9H2O. That's what's happening in this part of the picture. Over here, we're looking at an expanding gas pushing back the atmosphere. This does the PV work, which W equals negative PdV, which we see here in our formula. So here is just the system, and this is it in its initial state. After its surroundings, you see that it's expanded a bit, which is showing us how much gas is pushing back on the atmosphere. And from that, we can find out our PV work equation. So, thank you so much for staying with me for these 5 slides, and I hope you have a great day because I sure learned a lot, and I hope you did too. Bye.